So if we look at a simple schematic like this, we see that we have a few items of response that we might be interested in is the impact of mechanical loading. Then we also have water flow and also water pressure. In terms of FLAC, the way that we compute the impacts of mechanical loading on our soil skeleton is using the set mechanical on, and the way that we capture the stress strain response is through the constitutive models. I've mentioned this already, but then the other important thing we'll talk about is water pressure and water flow. In that, you can go through and show that the strain in the water is equal to the volumetric strain divided by the porosity. And so then what we see is that the change in pore pressure is equal to the bulk modulus of the fluid times the strain in the fluid, which can also be shown as just the bulk modulus of the fluid divided by porosity times the volumetric strain. And this is the equation that we utilize. Or maybe that is helpful, I think, in thinking through how pore pressures change due to changes in volumetric strain. So in that, there's two ways in which the pore pressure can change. First is through volumetric strain. This is captured in FLAC using the config GW of flow and assigning a fluid bulk modulus. So the way that we tell FLAC to compute these things is by having GW flow in the config, and then we also need to specify a real value for the fluid modulus. It's important to note that FLAC computes changes in water pressure from volumetric strain, regardless of whether or not we have water flow. So in terms of FLAC commands, that would be water flow is controlled with the set flow on or the set flow off. We'll talk more about that on the next slide. Another way that we can have water pressure changes, as well as focusing on fluid flow, but I'm focusing really, the emphasis here is on effective stresses, so we're particularly interested in here in terms of water pressure, is that water flow also changes pressure, as highlighted here. The way that we capture that in FLAC, the way that we can calculate that in FLAC is using both the, first we need to configure the analysis for groundwater flow, which is highlighted with the script here. And then also we're going to click set flow on. So if, for instance, we wanted to conduct a consolidation process, we would need the config GW flow and then also the set flow on so that we can calculate the movement of water and the dissipation of pore pressures with respect to time. Note that there will be no water flow, so you could think of this as like a fully undrained situation if you have the set flow off. In most dynamic analysis that I've conducted or I've seen others conduct in FLAC, typically we have the set flow off condition where we are not modeling the changes in pore water pressure, or where we're not modeling flow movement during shaking and also the dissipation process. It's certainly something that can be done. I think there's a few reasons behind that. One is, generally speaking, the analysis may take notably longer with the flow on command, and that has to do with the time step and also just the number of calculations required or the amount of work for each time step. That, and then I think also the challenges in accurately or in trying to predict the permeabilities in the various materials. So typically speaking, for at least two-dimensional dynamic analysis with seismic shaking, I've generally seen and I've generally done myself a flow off. There's certain situations where I've done that for academic settings or for certain projects, but generally speaking, the flow off. Okay, so that's that little part. Another important part is the calculation cycle. So here's the mechanical calculation cycle again. that part we've discussed and we've highlighted through various examples. What I also want to talk about is fluid flow calculation. We could certainly get into all the nitty-gritties, and I will point you to the various manuals if you're interested in this. I just want to highlight some of the key features. First up is that in terms of the element, we're using the same element, the same nodes, and in that, pore pressures are going to be calculated at the nodes. And with this quadrilateral element, the impact of that being is that there's going to be a linear variation in pore pressure in the zone or a uniform specific discharge in that zone. And the FLAC is going to be using finite difference and finite volume methods to approximate the governing equations. Okay, one important thing in terms of material parameters is that we are frequently used to inputting in the Darcy's coefficient of permeability and length per time. FLAC requires that we input the mobility coefficient, which is just that Darcy's coefficient of permeability divided by the unit weight. So important note. Okay, so for the FLAC calculation cycle with fluid flow. It is iterative once again, depending on where you start. You are going to calculate node flow rates from pressures. That would be Darcy's law. And then with those new flow rates, you were then going to calculate updates and stresses from flow rates and volumetric strains. And so this calculation cycle just goes around and around and around and around and around. So what we have now are two different types of calculation cycles. We have the mechanical cycle on the right and the fluid flow cycle on the left. And so each of these is going to pass information along during both calculation cycles. You'll see that the one part I have added in terms of the mechanical cycle, which was not included, is to calculate new pore pressure. But this is consistent, the mechanical cycle, with what we have seen before, and then the fluid flow cycle. So each of these could be occurring independently, and we can control that by the set flow on and the set flow off in terms of whether or not the fluid flow cycle, as well as set mechanical on and set mechanical off with the mechanical cycle. And so depending, one approach is that we could uncouple these analyses as we progress through the solution step. What we could also do in the case of, say, consolidation, we could also couple that. And in that, I've tried to highlight this kind of in a traffic type of sense with the flow of information as it goes along. And you can see that that pore pressure is going to get transferred back and forth between these two cycles. One item that we can control is the number of mechanical cycles for a fluid flow cycle or a number of fluid flow cycles for a mechanical cycle. And that would be with the NMEC and the NGW. So that would be the number of solution steps that we're going to conduct for each, which may be important depending on the type of process, whether or not we have significant changes in the mechanical process or the fluid flow process. So there's this coupling. A few other important items that I wanted to highlight, and that has to do with a few items that there's some additional numerical schemes available in FLAC to help us along with some of our tasks. Few of them. One is the saturated flash flow scheme that's provided. Command that I frequently use is the unsaturated flash flow. This is a very efficient algorithm that is going to allow the phreatic surface to be established. This is one that I have greatly utilized, and it definitely makes a huge impact in terms of establishing the phreatic surface in your embankment. Another one that I frequently use is the fluid bulk modulus scaling, and this is going to help with the calculation cycle where we have, and in the case of an embankment, where we have contrast and permeability as an example. And then also another one is the adjust total stress, which is the total stress will be automatically adjusted with pore pressure changes. So a few little schemes. Now, what I wanted to talk about now are two important items that I think are important considerations when we do these analyses. Some more important than others, but I think it's all pretty important. One is when we do this type of analysis, the considerations, what are some additional considerations in terms of the density, and then also the bulk modulus. So first, density. When we use the config groundwater, or for short, you could just type in config GW, FLAC starts doing something a little different. FLAC then views the density that we input in our analysis as the dry density. And then the density that's used in calculations internally, like let's say, for instance, to calculate the total vertical stress, is calculated using the dry density. It's assuming you're specifying the dry density plus the porosity times the degree of saturation times the unit weight, the density of water. Now, in some cases, that might be fine. So let's say you specify the dry density, and so you're going to have the dry density if it's fully dry. And then if you have a degree of saturation of 1 and all of that type of stuff, that's going to end. Then you specify your porosity as whatever you think it should be for your particular material. You're going to get a saturated density. I found that in most cases, we're not wanting to utilize our dry density, but we want to use our total moist density above the phreatic surface, and then maybe our saturated density below. And so that moist density, which doesn't correspond to a degree of saturation of 0, but in our FLAC analysis will correspond to a degree of saturation of 0, as we will identify, we have an issue. We'll talk more about the specifics of this when we actually calculate this, but in essence, what we need to do is that we need to back calculate what our density should be. Then we're going to specify that into FLAC, and we're going to trick FLAC to then produce the density that we want. We will identify this more in a moment. Another really important one is going to be in terms of considerations of both the water bulk modulus and the bulk modulus of the fluid of the soil. First is in terms of water bulk modulus. The main item here is that the bulk modulus, the fluid bulk modulus in, for instance, metric units is 2 × 10⁹ pascals. That is the bulk modulus of the fluid. However, that is the true bulk modulus of the fluid, but in certain cases, if we input that particular value, we may have a significant low time step, which we don't necessarily need. And what you can find is that, in fact, what is important is not as much that the bulk modulus of the fluid is 2e⁹ pascals, but instead that the bulk modulus of the fluid is much larger than the bulk modulus of our soil skeleton. Another way of saying this is that for computational efficiency, FLAC recommends that this RK value, which is defined right here, is less than or equal to 20. And so this is something, again, that we'll talk about later, but which we need to keep track of as well. The last important item is, well, what do we do about the bulk modulus of the soil skeleton? Well, in a total stress analysis, what we're going to do is that the pore water pressures are not going to be calculated, just the total stresses. But what we would like to do is, if we're going to do an undrained analysis, we want to ensure that the volumetric strains are quite small. In an undrained analysis, in theory, with Poisson's ratio of 0.5, but that's going to be problematic due to the fact that that would be corresponding to a bulk modulus of infinity. So often it's, say, around 0.45. Another way of computing that would be using the formula provided here, where the undrained bulk modulus of our undrained soil bulk modulus is going to be our drained bulk modulus plus the bulk modulus of the fluid divided by porosity. So in highlighting this, a few things that I wanted to highlight here, and we're going to go through an example, is first, it's important to think through the density. There's going to be some changes with respect to that. The other important thing is, if you're going to use a water bulk modulus, then you want to ensure that it's not too large. And 3 is that if you wanting to do a fully undrained total stress analysis, you need to be sure that you're using an undrained bulk modulus of the fluid. Otherwise, you should be doing the drain value.